Hello everyone, today I'll be working through question 1 from the Physics 457 practice final for the upcoming final exam. Question 1 asks, Heidi heroine in a spaceship trying to escape through a corridor. She is racing past the sinister snipers. So here are the two snipers and here's Heidi. She knows that the sinister snipers will fire at exactly the same time when the middle of her ship passes halfway along the corridor of space that they are guarding. So they're going to fire their two lasers at the same time. The sinister snipers are 70 meters apart in their rest frame, and the rest length of Heidi Heroine's ship is 110 meters long. So there's a lot of information there, and we'll kind of pick out in this diagram what's going on before we start answering part A. So we see that we have Heidi, and she is essentially in our spaceship. She's our object that's moving with some velocity v, and that v is unknown at the moment. She has a rest length of 110 meters in her reference frame. So the length of her spaceship in her reference frame is 110 meters. Now, the two sinister snipers are these two little people here that are going to be firing lasers at Heidi as she passes by in her spaceship, and essentially that they are situated at a rest length of 70 meters apart in the reference frame. And then it says, for part A, is how fast does Heidi Heroine have to travel to make it so that the lasers from the sinister snipers pass right in front of the nose of her ship and right behind the tail of her ship. So we want to know the velocity v so that when she passes these two snipers, when she passes the two laser beams, the length of her ship will have become 70 meters. So the laser passes directly in front and directly behind, sorry. So this is part A. So we want to find v. So right away, we know that this is going to be a relativity problem because she'll be moving with certain speed, and we want to see that her length is going to contract. And that's our first pointer right there. If you want to recall, we have Lorentz contraction, or length contraction, which says that when an object is moving with a speed that's close to the speed of light, relativity says that the length of that object will appear contracted. And the formula for that is given by delta x, the change in length, is equal to 1 over some gamma factor times the delta x bar, where delta x bar is the rest length of that object. So I always have trouble remembering this formula and remembering which side the gamma factor goes on top. This is the Lorentz factor. So the way you can kind of think about it is that we know objects are going to contract when they're moving with a velocity close to the speed of light, given the Lorentz contraction. So to me, what that means is that we have an object with a rest length, and that rest length will be decreased by the factor of gamma, which means we have to divide by the factor of gamma, where the gamma is usually going to be greater than 1 for speeds close to the speed of light. And then that would become our new length, delta x. So we know that delta x bar is our rest length, and it will be shrunk by the factor of gamma. So here, when we're trying to find v, we have to recall that v is actually embedded within gamma. So gamma itself is given by 1 over the square root of 1 minus v squared over c squared. So using these two equations, we want to try to find and solve for v. So we can say here, instead of using x and x bar, I'm going to use L. So I'll see that this is L naught, which I will define as L bar, essentially the rest length. And we want it to be contracted to a length L. So what I want is I want L to be 1 over gamma L naught. Or essentially, I want 70 meters equal 1 over gamma 110 meters. So again, I want that my rest length is contracted down to 70 meters. And we know that because we want it to essentially pass exactly between the two lasers of length 70. So I can solve this over, and I can get that essentially this will be gamma. So 1 over gamma, we'll put the square root on top. So I'll get the square root of 1 minus v squared over c squared is equal to 70 over 110. Now you can do some quick algebra, and you can find that 1 minus v squared over c squared is equal to 70 over 110 squared, and of course v squared over c squared is equal to 1 minus 70 over 110 squared. And bringing this all back up to conclude up here, we see that v is equal to the square root of 1 minus 70 over 110 squared multiplied by c. That'll be our velocity. And you can put that in your calculator, and I found that it was approximately 0.77 the speed of light. So going back to recap to what we were talking about, we see that we have Heidi, she's in her spaceship and she's traveling along and she has a rest length of 110 meters. She's moving at some velocity v. We want to determine v so that when Heidi passes in front of the two sinister snipers, that one laser and the other laser, which are fired at the same time, pass directly in front and behind her spaceship. So we need her length to be 70 meters after it's been contracted. So we know that the contracted length should be 70 and the rest length is 110. And from that, using the Lorentz contraction formula, we can solve for v, which is within the gamma term, within that Lorentz factor, using some algebra and setting up that we have the rest length is equal to 1 over gamma factor, the rest length times the 1 over gamma factor is equal to the new length that we're looking for, which is 70 meters. And then just doing some math and plugging in your calculator, we get that the velocity at which Heidi should travel with so that she passes directly between those two lasers when they're fired is 0.77 times the speed of light. So we'll continue on with part B of question 1, which asks, describe how Heidi observes the lasers passing her ship. Explain how her observation is the same or different as the observation of the sinister snipers. So we know that from relativity that the reference frames of the two observers will produce some different results. So if we start with the sinister snipers, we can see that they're 70 meters apart in their rest frame. And we know that they fire the lasers at the same time. So they will fire their lasers simultaneously. So those two lasers will move off in space at the same time, a distance 70 meters apart. And we saw in part A that Heidi was moving with a velocity of 0.77 c, so she's moving along, and the sinister snipers will see her length contracted down to 70 meters, and they will observe that she will pass directly between those two lasers that they fired simultaneously, passing one in front of the ship and one behind the ship. Now, we can find out quickly what the factor of gamma would be. The factor of gamma is 1 over the square root of 1 minus v squared over c squared, which gamma is 1 over the square root of 1 minus 0.77 squared. And we can see that this factor will be greater than 1. Just because this factor here will be less than 1, take the square root, 1 or something less than 1 is greater than 1. So what that means is that because of relativity and because of the change of reference frame, as Heidi passes the sinister snipers, she will also see their length contracted. She will see the separation between those two snipers to be a smaller distance. So even though they are the ones that observe her with a now length contracted rest frame or length of her spaceship to be 70 meters, she will also observe them contracted in length. So she will observe them to have some sort of length or distance between them equal to 1 over gamma times their rest length. So their length will be 1 over this gamma factor multiplied by 70 meters. And you can check in the solutions what that actual value is. You can solve for gamma using your calculator, plug this in, and I think it's somewhere around 44 or 45 meters. I didn't do the calculation, but I remember looking at the solutions and seeing what it was. So what that means is that as Heidi passes by those two snipers, she will see the distance between those two lasers to be approximately 45 meters, approximately 44 meters, as I've written down here. So she will not observe them to be the same distance apart as the sinister snipers. So that's a different observation. Additionally, because of the difference of simultaneity in the two reference frames, she will observe this laser on the right being fired first, and the second laser, the one behind her, observed at some other time. So as she moves along, she will see this laser being fired, and then she will move a little bit forward, and then she will observe the one behind her being fired. So in her reference frame, those two laser beams are not simultaneous. And that's a difference in simultaneity between the reference frames. So again, just to recap quickly, these two sinister snipers will observe the laser beams being fired simultaneously, a distance of 70 meters apart. And as Heidi passes by, she will observe the two laser beams at different times. She will observe the one in front of her first, and then she'll observe the one coming up behind her after she passes the first laser beam, and she'll see them a distance that's been length contracted to somewhere in the 40 meter range. And that's the answer to part B. So we'll wrap up question 1 by answering part C, which says that the snipers have a long line of positive charge lying along the same direction as Heidi is traveling. The line has a constant charge density and is long enough that it can be considered infinite. The snipers observe the electric field is E, electric field E is given by K over S hat. This is part C. And the magnetic field is equal to 0. And when you see this is our line of charge, and we can say that this is the positive z hat direction. And we know from part A that the velocity at which Heidi is traveling is 0.77 c. Okay, so part C asks, Heidi is traveling in the positive z hat direction. What E and B do Heidi Heroin measure from this charge distribution? So relativity tells us that because she's moving close to the speed of light, she will observe a different electric and magnetic field than the sinister snipers do. So the sinister snipers observe these magnetic fields, this magnetic field and this electric field, these electromagnetic fields. And Heidi, the one traveling observer, will observe something different. So a good place to start with these questions, which apparently I didn't start with, but we'll start with that quickly here, is to find gamma. So we know the velocity v, and we know that the Lorentz factor gamma is 1 over the square root of 1 minus v squared over c squared. So we can plug this in and say that we have 1 minus 0.77 c squared, 0.77 squared over c squared. And we can find this out to be 1.57, approximately 1.57 if you put that in your calculator. The c squareds will cancel. You can plug that into your calculator and get 1.57. The reason I want to solve for this gamma factor, probably should have done it in B as well, but it's a good value to have just in case you ever want to kind of express some sort of Lorentz contraction or some time dilation, or as we started in part B, we saw that Heidi also observed the sinister snipers to be contracted in terms of their length. So this gamma factor is something that's good to calculate right away. So given that we know what V is, maybe we can just start the problem by figuring out what gamma is, and then even if we don't use it, it's just a quick little calculation to figure out a quick number. So if you don't use it, it's not a big waste of time, but if you do have to use it later, you have it. So the reason we want to use gamma is because we can recall that relativity affects the perpendicular components of both E and B. So we recall that the electric field, the perpendicular component, and this formula is on your formula sheet, the electric field component from now the observer that is moving, so we put a bar over top of the electric field, is given by gamma multiplied by the electric field of the not moving reference frame minus the velocity at which they're moving with crossed with the magnetic field. So again, here we have an E bar, where the bar denotes the fact that this will be the electric field that Heidi observes, and she is the moving observer. And additionally, the magnetic field will have a perpendicular component given by gamma. Again, this is B bar, B perpendicular bar is given by gamma. And then the B field perpendicular of the stationary observer plus 1 over c squared, and then V cross E. Again, the velocity of the observer and the electric field of the initial frame. And the parallel components will be the same. So any change electric field observed along the line of motion, along the same vector direction as the Heidi is moving, will cause no change in electric field, but the perpendicular component will be observed differently. And these two equations are on your formula sheet, but they're also equations 12.109 in Griffiths, if you want to go look in the textbook to see that for yourself. That's where I found them. So now we know that the velocity is in the z hat direction, and we know that the electric field will be moving radially outwards from this line of charge. So we'll say that the radial direction is S hat. So S hat here is indeed perpendicular to Z hat. So Heidi is the moving rest frame, so we want to determine what electric field and what magnetic field she observes. So we can do this just by calculating these two equations. So we see that E bar perpendicular vector, so it's hard because you always have to put the vector on top of the electric field as well, because it is an electric field vector, so you have to include the bar and the electric field, is given by this equation here. So we see that we have 1.57 from our gamma multiplied by our initial electric field, which was K over S hat, minus V cross B, but of course B was 0, so this is just minus 0. So we find that the electric field that Heidi observes, E bar, is given by 1.57 K over S hat. Yes. Okay, so now the magnetic field component that she observes is given by gamma, so 1.57 multiplied by the magnetic field observed originally, which was 0, plus 1 over c squared multiplied by the velocity, which is 0.77 c in the z hat direction, crossed with the electric field, which is k over s hat. So we can pull everything out and we get 1.57 times 0.77 c over c squared, k over s, and then our vector component is z hat cross s hat. And working through, we can plug in the values that we know, and we can calculate through that we get, we draw a line here, this should be approximately 1.21 k over s times c. The c and the c will cancel, and you can multiply those two factors out with your calculator. 1.21 k of cs, and then z hat cross s hat, I believe, is phi hat, if we know that s hat cross phi hat is equal to z hat. You can check that right-hand rule at home. So this is our B perpendicular. So B bar perpendicular. Again, that bar denotes the fact that it's Heidi observing it, and she is the moving observer. So we can conclude that in this problem we have found the electric field and the magnetic field as observed by Heidi, who is the moving observer. So in the stationary reference frame, we see that we have a radial electric field, k over s hat, and no magnetic field as observed by the sinister snipers coming off of this line of charge, which is pointing in the positive z hat direction, aligned in that axis. We calculated gamma using the velocity that we found in part A. We found it was to be about 1.57. And then we used the two equations from our formula sheet that recalling the fact that a moving observer, due to relativity, will see a changed magnetic and electric field, given that there will be some sort of contribution from both components in the new measured field. So here, the new electric field depends on the previous magnetic field, and additionally, the new magnetic field depends on the initial electric field and magnetic field. So there's the two different components. And then you can just plug in your values, do some calculations, and end up that you have this electric field, E bar, the magnetic electric field that is observed by Heidi, and then this is the new magnetic field observed by Heidi as well, also B bar perpendicular, and these are two vectors, so we need the direction included as well. And that concludes part C of question 1 and the entirety of question 1.